Our third speaker is Mr. Shim from Wyoming. Shim is the bridge management engineer at Wyoming. He's responsible for the implementation and operation of the bridge management system there. Also the generation of models for deterioration, for improvement in cost, and for optimization of strategies for maintenance. He has produced comparative life cycle cost analyses for Wyoming DOT's bridge deck overlays, and he's currently working on developing multi-objective optimization routines to produce tools for trade-off analysis. Mr. Shim.
Good morning, everyone. I'm going to present about the allocation of bridge deck preservation budget using optimization process. First, I'll briefly overview about the general concept of optimization process and discuss about models, bridge management system models, which are needed in optimization process. Then I will implement about the single objective optimization using two different scenarios. And finally, I'll briefly introduce about multi-objective optimization. Optimization usually compare deterioration with improvement along with associated cost to achieve its objectives. And it determines what percentage of budget should be allocated for specific preservation actions. And it is done at network level, and specific bridges are to be selected at project level using the result of budget allocation. There are several components needed in optimization. The most important component is the bridge management system model, which include deterioration model, improvement model, and cost model. In YDOT, we use the MBI deck condition rating data to model the deterioration and improvement. And we also need the objectives for the optimization. It can be the maximizing bridge performance measure, or it can be the minimizing the annual budget. And it's usually constrained optimization, so we need a constraint. It's usually given annual budget, or it can be agency's policy, or it can be target bridge performance. And we need economic factors. Well, this figure shows the general concept of optimization process for the budget allocation. This circle represents total deck area with specific MBI condition ratings. So adding up all of this area will represent the total deck area owned by YDOT. By saying that this red arrow below is the deterioration flow, and the green arrow above is the improvement model. In YDOT, we have every MBI condition rating has a specific link to the preservation actions, and each preservation action has an associated cost. By establishing this, optimization compare deterioration with improvement, trying to put the fund each of different preservation categories in order to achieve whatever the objective is. So this is the general concept of it, and this is the typical result of optimization. Well, in this example, 39% will spending on minor rehab and 36% will spending on major rehab in order to achieve the objectives. We're going to discuss more about this. And let's talk about the bridge management system model, starting with deterioration model. YDOT used the historical MBI deck condition rating data for deterioration modeling. Well, as we all know, MBI condition rating represents the current evaluation of bridge deck condition compared to as-built condition, and they are scaled from 0 to 9, with 0 means failed conditions. And rather than having some deterministic modeling, YDOT used the probable duration model that remains in each of MBI condition ratings. And using duration model, and we produced the Markov chain deterioration model. And there will be two different deterioration modeling. One for the deck without rehabilitation history, and one for the deck with rehabilitation history. So this is the probable duration models that remains in MBI condition rating through 7 to 3. This is for the bridge deck without rehabilitation action before. And this is the probable duration for the bridge deck with rehabilitation history. As we can see, the duration is reduced significantly. And using these duration models, we can generate Markov chain deterioration model, and this is it. And the green line is the pure deterioration without rehabilitation history, and red line is the deterioration after the rehabilitation. And next model is a cost model. Cost model usually estimate the cost associated with preservation actions. And they are developed by analyzing historical rehabilitation as well as new construction cost data. And we also use probabilistic approach rather than the deterministic cost, and they are renewed annually. So this is our probable cost model. In WIDA, we have 4 major preservation actions: repair, minor rehab, major rehab, and replace. Minor rehab is sort of proactive preservation action, as we typically apply those actions for the bridge deck with early stage of service life. Major rehab is kind of reactive preservation actions, and we typically apply them for bridge deck with MBI condition rating 3 or 4. So last model is our improvement model. And this model simulates the effect of preservation action in terms of increasing MBI condition rating at network level. And they are developed by analyzing historical rehabilitation data, and they are also in the form of Markov chain model. So here is a typical example. The first column shows the MBI condition rating before the preservation action. And first row is the MBI condition rating after the preservation action. For example, if we apply preservation action for the MBI condition rating 5 bridge deck, and 53% will increase the condition rating to the 7, and 47% will increase the condition rating 6. So using this information, we can build the Markov chain improvement model. And network level, if portion of bridge deck receive the preservation action, we're going to use this model to predict the future. And otherwise, we're going to use the deterioration model. And other piece for the optimization is the objectives and constraint. The left side figure shows the single objective optimization. Left y-axis represent the objectives. For example, minimizing structural deficiency. By manipulating optimization variable means optimization try to allocate the fund on various preservation actions. By doing so, we get to the minimized point, which is the achievable structural deficiency. In this case, we need to have a constraint as the given annual budget, or I call maximum allowable annual budget. Or objective can be the minimizing annual budget. In this case, we achieve the minimized annual budget in order to achieve the target structural deficiency. The target structural deficiency in this case is the constraint. So I guess we are ready for the implementation. There will be 2 scenarios, and first one, objective function will be the minimizing structural deficiency. The constraint, as an example, we are going to use $20 million, and planning horizon is 10 years. Our agency policy, to replace the deck for condition rating equal to or less than 2 prior to other preservation action for the safety purpose. If we implement this, this is the projection of structural deficiency for the next 10 years. We're going to spend $200 million, and we're going to reach the structural deficiency around 2%. Right now, YDOT has 11% of the structural deficiency in terms of the MBI deck condition ratings. And this is the NPRM measure. As we see, the green line is the good bridge decks. There is a little bit increasing pattern for the good bridge deck and definitely reducing pattern for the poor bridge decks. And in order to achieve this kind of projection, this is the result of the optimization. We have to spend the budget in this pattern. And first year, we're going to spend 84% for the major rehabilitation and another 16% for the replacement. As we see, 100% of our budget will going to only structurally deficient bridge decks. And this is the last year of the budget allocation. Unlike first year, we're going to spend 47% for the minor rehab, something called the proactive preservation actions. And if we spend more money, then this portion will increase. So I try to vary the annual budget. So what this shows that the animation by varying annual budget from 20 million to 30 million, we're going to reach the 0% structural deficiency soon. And this is the NPRM measure by varying the annual budget. The second scenario, the objective function is minimizing annual budget. The constraint is a target structural deficiency. We're going to achieve the 6% of structural deficiency during 3 years, and then maintain that structural deficiency during the planning horizon. And this is essentially spend as minimum as possible annual budget to achieve the target structural deficiency using agency's policies. So if we implement this, this is our target structural deficiency. According to the optimization, you're going to spend $165 million to maintain this. Well, it's definitely 35 million cheaper than scenario 1, but there is good and bad for this. So this is the required annual budget. Annually, we require this pattern of budget. And this is the NPRM measure for the scenario 2. Unlike scenario 1, the good bridge deck is kind of decreasing mode, and poor bridge deck is kind of holding. Well, in terms of the health of network of bridge deck condition, I kind of prefer the scenario 1. So this is the first year budget allocation for the scenario 2. And as we can see, 82% we're going to spend for the major rehab, and another 18% we're going to spend for the replacement. This is the last year of budget allocation. There is a big difference between two scenarios here. Well, at the end of planning horizon, we still have to spend 100% of our budget for the structurally deficient bridge decks. So we're going to save $35 million, but there is some difference in terms of health of bridge decks. In single objective optimization, somehow it produced the focused result to this objective function as we expected. And there is only one solution point at each year. Therefore, there is no trade-off analysis for the single objective optimization. And we definitely want balanced solution point between objectives in certain level at the same time. In order to do that, we need to implement the multi-objective optimization. And there will be multiple solution points which satisfy optimality condition. I can compare two optimization schemes here. Right-hand side figure is the single objective optimization. Since there is only one objective, we get only one solution point. left-hand side figure is the multi-objective optimization. Let's say there are two objective functions. X-axis is the annual budget, Y-axis is the structural deficiency. Well, unlike the single objective optimization, we're going to have a bunch of solution points represented by the red curve here. So, well, I try to do the multi-objective optimization using Y-DAS total depth area. As we can see, the X-axis is the annual budget, Y-axis is the achievable structural deficiency. So structural deficiency is now expressed as a function of annual budget, and this can be very useful for the decision maker to make their decision. And there is also useful information here. There are two reasons in these figures, and first reason is slope is steeper than the second reason, which means we don't need to spend a lot of money to reduce the structural deficiency. So if there is a flexibility on annual budget, it's probably better to pick the point around $40 million. And if we do the same thing for the second year and third year, that's probably economical way to reduce the structural deficiency. The Y-DAT just finished developing the multi-objective optimization algorithm, and we are planning to use it starting next year. This is the end of my presentation. Thank you.
Yeah, when you were putting together your costs, how do you differentiate between the cost of maintenance of traffic for repairs versus, because that can vary based on whatever type of road you have in terms of usage?
When we try to build this cost model, this cost model does not include the mobilization or traffic control. This is directly related to bridge work.
Anyone else?
I've got a question. When
George does.
Chris took the mic, I thought you had a question. I didn't realize you were taking it away from me. It's okay, I got this one. So several things, but one that caught my eye, and this chart caught my eye too, but I'll do that second. You had your duration models in terms of MBI general condition ratings.
Yes.
And it appeared from the curves that there's less dispersion, less variance at the poor condition states. Can you comment on that? Those.
Okay. This duration model, I used the bridge, I extracted bridge, which exactly has 2 times overlay conditions. And so between those 2 letting days for the overlay, and I call it as a duration of the overlay. And using those durations, I'm only using the uncensored data. So as we going down condition rating 3 and 4, it's the DOT's decision to decide redo the overlay. So I guess it's the variance is kind of getting reduced.
Because the bridges are being taken out of, the decks are being taken out of that condition rating.
Right.
As you went through costs and then the budget for the state to reduce structural deficiencies or to get it to exactly 6% or so forth, I was having trouble following what the values are. It looked like something around $30 million a year would eliminate SDs, and $20 million a year would keep you here at 6. Are those the right values, or can you comment on the values?
This one?
Yeah.
Well, each year, the optimization required different annual budget, and this graph shows that difference in order to keep these structural deficiency patterns.
So around between $15 and $20 million to get to 6.
Yes.
When you went to your multi-objective optimization, it looked like some other budget had shown up. The values seemed very different. So 6% here is what, 30 million? That's what I couldn't understand.
Well, this is the first year optimization. So I reached the 6% during 3 years.
Okay.
And this is just, if we want a 6% next year, we have to spend this much.
Okay, that's great.
Okay.
More questions for Mr. Shim? Mr. Shim, thanks so much.
Thank you.